I'm going to talk about a specific differential equation type. I'll assume that you know what a differential equation is. If you don't, I would invite you to watch my introductory video on differential equations. Okay? So the differential equation type that I want to focus on is the following. This says that the derivative of a function is equal to a constant times the function itself. Okay? The function can be a function of x, could be a function of t, or any other independent variable. Okay? If it was a function of x, this is the general solution. Y equals a times e to the kx. So take the derivative of that. I'll do it also. And we get ak times e to the kx, which is equal to k times a times e to the kx, or ky, right? So that is a valid pattern or set of solutions. If your function was a function of time, then the solution, the general solution, would be some constant times e to the kt. And that, of course, would also satisfy the differential equation if it was a derivative, if it involved a derivative with respect to time. Now, let me show you a problem where this differential equation shows up. Suppose that some biologists discovered that a culture of bacteria was growing, the population was growing such that the population obeyed the following differential equation. P prime equals Kp. So the rate of change in time of the population is equal to some constant times the population. Furthermore, we know that if we start with 1,000 bacteria, then 4 days later we're going to have 2,000. So we have 1,000 at time 0 days, at time equal to 4 days, 4 days later, then we'll have twice as much, 2,000. All right. So the biologists come to us and say, can you find a function that models the population of this bacteria? Okay. So we would maybe first say, aha, this differential equation is a form that I'm familiar with. So the population must equal some constant times some exponential times kt. Okay? And then we use what we are given. We know that we start with 1,000. So what does that mean that we start with 1,000? That means that when t is equal to 0, p is going to equal 1,000. That's what the population is going to be. So if you plug in 0 to the function a e to the kt, you get a, right? Because the exponential evaluates to 1. So we just determined what a was. Now, if t is in units of days, then we also know that p of 4 is equal to 2,000. And let's evaluate the exponential for t equal to 4, and let's substitute 1,000 in for a. So 1,000 e to the 4k. Okay? And now we just need to solve for k. So if I, let's see, if I divide the 2,000 by 1,000, I get 2. So 2 is equal to e to the 4k. If I take now the natural log of both sides, I get that the natural log of 2 is equal to 4k. So k is equal to the natural log of 2 divided by 4. And now I can express the function that the biologists are looking for. So what do we have? We have 1,000 times e to the, ln of 2 divided by 4 times t. Now let's see if we could make that look less threatening. Okay, so let's do this. That's equal to e to the ln of 2, all of that raised to the t divided by 4, right? Okay, e to the ln of 2, that simplifies to just 2. So 1,000 times 2 to the t divided by 4. That's probably as nice as we could make it for the biologists. So go ahead and plug in 0, you'll see that you get 1,000. Plug in 4, you'll see that you get 2,000. And you'll take the derivative and you'll see that that satisfies the original differential equation. Okay? So we, in summary, found the general form. We knew the general form once we identified the differential equation type, and then we just had to solve for a and k. All right. Here is another field, another example where this differential equation would come up. So the rate of decay of radioactive bismuth-210 obeys the following differential equation for some constant k. All right. Let m denote the amount of mass of radioactive bismuth-210, and let m prime denote the rate of change with respect to time of the amount of mass of radioactive bismuth-210. All right, so the time derivative of m is equal to some constant times m. Now, not only does the decay of radioactive bismuth-210 obey that differential equation, but it's also known to have a half-life of 5 days. Now what that means is that every 5 days the amount of mass decreases by 50%. Okay? So if we start with 800 milligrams, can you determine a function that describes the mass m t days later for any value of t greater than or equal to 0? Okay, that's the challenge. So pause the video now if you like and try to solve for the function m. Okay, I'll go ahead and work it out as well. So this differential equation is the same type as what we've been discussing. So m must have the form a equal to kt for some a and k. And we know that we start with 800 milligrams. So m of 0 is equal to 800, which is equal to a. All right. And how many milligrams are we going to have 5 days later? Aren't we going to have half of what we started with? So m of 5 is equal to 400, which is equal to the function m evaluated with respect to t equal to 5. So let me write what that would give, and I'll substitute 800 for a. And then I have 800 multiplied by e to the 5k. Okay, so now we can solve for k. So let's divide the 400 and the 800 e to the 5k by both of those terms by 800. So then I'll have 1/2 is equal to e to the 5k. Now let's take the natural log of both sides. Okay, now let's divide both sides by 5. So k is equal to 1/5 ln of 1/2. By the way, the ln of 1/2 is equal to minus the ln of 2. So I can write that as minus the ln of 2 over 5. So the function that we're looking for apparently is 800 times e to the minus ln of 2 over 5 times t. Okay, and we can simplify that a little bit. Let's do this. Let me write the exponential part as e to the ln of 2 raised to the minus t over 5 power. Convince yourself that that is equivalent. So e to the ln of 2 is equal to 2. So the nicest I could probably make this is 800 times 2 raised to the minus t over 5 power. Okay, so if you plug in t equals 0, you'll see that you get 800. If you plug in t equals 5, you'll see that you get 400. And also you can take the derivative with respect to time and convince yourself that that function obeys the original differential equation. All right?